find roots of polynomials. And remember, this is how we find an answer to this problem. We call the answer to that problem a root of that polynomial. And people were coming up with these wild formulas. This is the formula that they found for what we call a quadratic polynomial, a polynomial of degree 2. But they found a formula for polynomials of degree 3. And they got real complicated really fast. If you want to see a formula for a polynomial of degree 3, you can look at the top of that thing. That's one of 3 answers. There are 3 different roots, differing by a few things. There's a couple more programs. So you can see they get crazy. And they found a 4th degree, which is even nutsier than that.
Nutsier.
And they looked for years to find a 5th degree, and they couldn't find it. And about 300 years after this guy published the 3rd degree polynomial in the mid-1500s, someone named Hegel discovered that it's impossible. Not only have they not found a formula for a 5th degree polynomial, but they can't. It's kind of cool that it took 300 years between the posing of that question to the answer to that question. And that all happened, that all resolved itself 200 years ago, or 250 years ago, 150 years ago. So it's kind of an interesting history. But anyway, trying to figure this out, trying to solve equations like this, sometimes some of the things that would be inside these roots would end up being negative numbers. And with quadratics, it's not a real issue, but with cubics, you can actually get real roots. In other words, that's not a cubic. You can actually get real number places where this thing crosses that stem from square roots of negative numbers. And it was kind of freaking people out for a while until someone just said, hey, let's just say that there is something like this. So consequently, the square root of negative 5, for example, we'll just think about that as equal to the square root of 5 times the square root of negative 1. And we'll just say, well, that can be equal to I times the square root of 5. We'll just represent it that way. We'll just say, well, what if there is a number that works that way? And we'll just put it there. And it sure enough turned out that a lot of it made things work. It made things work really well. So here's a real simple quadratic. X squared plus x plus 1 equals 0. And using the quadratic formula, you can see we end up with this kind of an issue, where we end up with the square root of negative 3 in there. Even weirder, it turns out that if we treat this, well, we'll treat one of these 2 answers. Notice there's 2 answers. There's negative 1/2 plus the square root of 3 over 2, negative 3 over 2, and negative 1/2 minus. There's 2 answers there. If we treat one of those answers just like we would treat it if it was regular numbers, we find that this thing even checks. So the first thing that we do, if we're checking one of those 2 answers, is in the place of x squared, we put this big mess squared. In the place of x, we put the mess again and 1 there. And we're going to just hope that this whole thing will work out. Once I do all this math, it'll work out to 0. And sure enough, it did. Foiling the top one out, instead of just writing it as this thing squared, I write it as this thing times itself. You get negative 1/2 times negative 1/2. You get 2 of these negative root 3 over 2. You get this times this, which is right here, and then you get another one, this times this. So you get 2 of those things. And then finally you get negative square root of 3 all over 2 squared. That's just the FOIL. That's just the old FOIL that you're used to, that you've seen a lot of times. And then simplifying it down, this thing simplifies to negative 3/4. And these guys, negative this and positive this, end up killing each other, and you end up with something that works out. So the math worked out. Yes, ma'am. All right.
Just the focus, just a little.
Oh yeah, I'm sorry. Sorry. Anyway, I'm not going to make us spend a lot of time dealing with the hassles of foiling such a difficult thing. That's a lot of work. But I just wanted to kind of put this up here so you can see that, yeah, yes indeed, if we allow this square root of a negative number to exist, it lets us solve problems that we weren't able to solve before. So that's the reason that we propose the existence of this thing, this I. Fine, that's cool. Next problem was, well, where do I put it? Where do I put I? If you think about it, you can't really have I be a negative number, and you can't really have I be a positive number. If I think about the real number line, there's 0. I can't put I over here because if I squared that, it would be a positive number. I can't put I over here because if I square any of these negatives, it should be a positive number. Where do I put it? Where can I put it? Well, the answer was found in kind of thinking outside the box. Instead of putting it on the real number line, they said, let's break out into a different dimension. We'll put I right there. We'll put I right there. And usually complex numbers are visualized as a plane.